Hey, welcome back. Today we're going to be talking about how to write equations for graphs for simple harmonic motion problems. And this is specifically for AP Physics C Mechanics students. So this is from 2012, FRQ number 1, and I'm going to talk you through how to do this. This is a really crucial skill. I'm convinced almost all AP Physics C Mechanics students need more help and practice with this. What I mean by that is if you're given, say, this graph right here, how would you go about writing the function for that graph and do related problems? So that's what we're going to be covering today. In fact, this is an important lesson also because it's covered by AP Classroom's daily videos, but I'm going to take a little more time to cover it and show, as I write out my thinking, how to think through these ideas and show you in a different style format. And just very quickly after this intro slide here, I'm going to write things out and explain my thought process in a little more detail than you see from one of their videos. So the first thing we're going to do is take a glance at this. I'm not going to read all of this at you, this wall of text here. It's just an intro part to the problem. Honestly, there's really not much that stands out from this long paragraph on the left. If you want to pause and read, go for it. But the summary is you just have a mass on a spring, and the mass on the spring is going to vibrate back and forth, oscillate back and forth. And we want to write the equation for this graph right here and solve related problems. So effectively, that's what we're going to be doing. I will talk you through how to think about these strategies and practice the key skills you need to be able to be successful on the AP Physics C Mechanics test. Let's go ahead and get to it. Okay, so looking at the left side of the screen over here, the first part of the problem says determine the equation for Vt, including numerical values for all constants. So I'm going to talk you through this, but this is the part where we need to practice our skills in terms of writing equations from functions, from graphs that you'll see given to you. So I want you to think about some of these key things. You may already know this, but you may need to get a little refresher here. I want you to think about some of these functions here. Let me zoom in and see if I can do that without losing that. All right, so here's what we're going to do. There are a few things we can think of in terms of modifying an equation. One is we could put a coefficient out in front here. If I were to type a 2, I want you to anticipate what do you think we would see as a result if we had a 2 as a coefficient out in front of the sign x? Well, what that's going to do is double the amplitude. Let's think about why that is. It's almost like we're doubling what this sine x can be. Remember, and this is really crucial, sine x, sine of some value, is just going to oscillate between 1, positive 1, and negative 1. That's the maximum values that you can have. So if you were to put a coefficient out in front of, say, 2, you're actually doubling the possible values that you can end up with, which would mean that your amplitude is going to double, right? If instead you had like a 0.5 or something like that, that would reduce the amplitude to half of what it was before. So your y values will oscillate between positive 0.5 and negative 0.5. So that's the first thing to know, is what this coefficient out in front will do for us. Another thing to know is what will happen if we type in a, say, 2 right here in front of the x. What do you think we will see? Well, what we're going to see is a doubling of the rate at which that x changes, right? So you're going to have a half of the period, so to speak, or a doubling of the frequency, depending on how you want to think of it. It doubles the rate at which the x value changes, right? That's one way to think about this. It's important for you to know how to think about these things. I could ask you one more before we get to something else really important. What if I put a 2 out in front of the y? What would you expect to see for that? Well, what you're going to see is you can think of that 2 as being applied as a 1/2 over here. And so the amplitude is going to be 1/2 of what it was before. In other words, this equation that you see right here will be the same as 0.5 being out in front here. Those are the same equations. All right, so those are all things you should know and be willing to play around with. If I haven't said it yet, I highly, highly, highly recommend that you practice with Desmos Graphing Calculator before you take your AP test and just get familiar with this, remind yourself of some of these key ideas. The other thing that I want to say is which of these functions, the sine or the cosine function, starts at the maximum displacement, like the amplitude, and which starts at the minimum. What do you think? Okay, well, the sine function starts at 0. You can see the red line right there starting at 0. and the cosine function starts at the maximum displacement from equilibrium, or you could say at the maximum amplitude, so to speak. So that's really crucial to be aware of as well. And I want you to think to yourself, all right, what is happening on the left? So now glance to the left at that equation that you see over there. First of all, you want to ask yourself, all right, is this going to be, will it be easier to work with a sine or a cosine? By the way, you can offset them with a phase shift. If you want more information about phase shifts, I'll put a link in the upper right about now. But at this point, what you can do is ask yourself, all right, are we dealing with a sine or a cosine? Would I prefer to write this really as a sine or a cosine function? And what also do you notice? Well, you can see that the data starts from 0. So if we're going to start here, we could just say the data starts from 0, so I'm going to work with the sine function here. But another really crucial thing to think to yourself is, what's different? What's different about the red function on the right-hand side and the black line that you see on the left-hand side? Well, it turns out that they are mirror images of each other in terms of opposites. I will say the amplitude is also different. We'll get to that in a minute. Well, what we're going to need to do is put in a negative sign in front of that. Let's think about that. If you apply a negative sign to this function, notice that right at 0, the function on the left-hand side is going down at time equals 0, and then we also have a function that's going down at time equals 0. To get that to work, you need to throw in a negative sign into your functions. In any case, let's go back to the screencast and I'm going to write some ideas out. Okay, and so as promised, let's think through this line by line and think about how to do this. So it says determine the equation for Vt. We already figured out that this is going to follow a negative sign format. So we'll say velocity, or velocity with respect to time, is equal to minus sine. We do need to follow a format that we have. This I'll just say is omega times t. T needs to be in there. It's a function of time. Your angular frequency needs to be in there as well. And we need to put a maximum value out here. So we'll say this is V max out in front. So let's rewrite this. We'll say Vt is equal to negative V max times the sine of omega t. Alright, so that's how we're going to do this. I do want to point out a couple things. This may be a bit of a mystery why we need to have a Vmax out in front. I've done a screencast on this recently where we derive this velocity equation from a given equation. Let me write the given equation that you see. So this I've done a whole lesson on. This is what you're given. Okay, so this is a given equation right here on equation sheet. Okay, and if you take the derivative of this, you can end up with a version of what we've ended up with up here. So this is a whole nother lesson, but that's the general equation that we're going to need to be able to get this. By the way, that's going to get you 1 point to be able to write this general equation just based off of the derivative and knowing some of those ideas to put in. By the way, there's no phi value here, there's no offset, so we don't need to worry about that. We don't need to put in the plus phi into the general equation here. Okay, so then what else can we find from this equation? Like specifically they say including numerical values for all constants. So that tells us something. There are other things we need to solve for. Well, one thing we can do is try to figure out the time. You see wavelengths here. Let me back up for a second and say you can see a wavelength here. This is one wavelength, but what is the time for one wavelength? Just one cycle, one wave cycle. What is that time? What do we call that? Well, we call that the period, right? So to be able to detect our period here, let me use a different color and label what we have. So we have a little more than 0.5 seconds, and that is for right here, right? A little more than 0.5 seconds. And then off to the right, we have a little more than 0.12 seconds. So that is the time differential for one complete wave. We said that's a period. So we do have to say that a period is equal to 0.7 seconds. That's an important idea, and that will give you 1 point as well. And that's just kind of straight from the graph, and it's an important skill to be able to solve these problems. And immediately you're going to get a point. And then you want to think to yourself, all right, they've given us something where we can interpret and get the period. what do we do with that? Well, really crucial equation that's on your equation sheet, a big part of it is going to be this. The period is equal to 2 pi over omega, which is another important step right here. We know that we need to have omega in our equation, and they're asking us to come up with specific numbers. So let's solve. We already know what t is. 2 pi are just constants. We don't know what our omega is. So let's solve and isolate for omega. So that would be 2 pi over the period, right? And if we do that, we end up with an omega is equal to 9 radians per second. So that is crucial here, and that's also going to get you one more point. And they're not that hard of points to get. Once you start practicing this and getting used to it, if you know what you're doing and you know what to look for and you anticipate what's going to be happening here, these are not that tough of points to get, honestly. Okay, and there's one more thing that we need to address. So this is, let me remind you, this is like our general equation. I'll label it as our general equation. We want to get to a more specific equation. So let's think about what else we have still in there to discuss. We also have a Vmax value, right? And so is there any way we could get our maximum velocity? What do you think? Take a look at the graph. Okay, and so hopefully you're able to notice that we actually can get velocity here. It's not the easiest thing in the world to read. Hopefully you get a better graph than this on your test. Actually, I guess that's readable. It effectively is going to be 0.16 right here. And so that's our maximum velocity. So let's write our specific equation. Okay, so we're going to write velocity with respect to time is going to be equal to minus our Vmax is 0.16 meters per second times the sine of, and in our parentheses here we need to write our omega as 9.0 radians per second, and that is times time. That's how you're going to go about doing this. Hopefully you can think through this enough that you can be ready to do this on your test. I actually think that there's a good chance you're going to see a problem like this. Alright, let's continue with the rest of the problem. Okay, and so taking a look at part B, it says given that the equilibrium position is at x equals 0, determine the equation for x, like position with respect to time, including numerical values for all constants. Okay, so let's think through how we're going to do this. This really is testing whether or not, at least the most direct way to solve this. There are a couple different ways of solving this, but I think the most direct way of solving this is to think, well, I know that the integral of a velocity equation is going to give us the position equation. So that's what we're going to start by doing. And I really want to stress that you have these two equations that I have taken a snip of and put in here. And notice, because we're dealing with a sine equation, we're going to use this rule right here. Please make use of this equation. Notice you're going to have on your equation sheets multiple pages, but one of the pages will have a calculus section where you'll find this. It's easy to make a little error, especially when you're stressed for time and so on. So like forget a negative sign or something like that. So please don't do that. Take a look at that and just make sure you're writing it correctly. So let's go ahead and do that together. So we're going to say this is x with respect to time is equal to, now because we're taking the integral, we can move out this constant out in front, 0.16 meters per second, and take the integral of sine, and then inside the sine function we have 9.0 radians per second times time, and that's going to be dt. Okay, so very good. So again, we've got this rule to follow, so take a close look at the rule. And what we're going to need to do is notice that the integral of sine will give us an answer of cosine. So we'll get there, but first let's do 0.16 meters per second. And notice we have a 1 over a, and that a is the coefficient. Well, what's our coefficient inside that sine parentheses? Well, that's going to be 9. So this whole thing is over 9 radians per second. Now the radians kind of go away. The per seconds cancel. The radians are sort of there as a label, but not truly there as an algebraic unit. They can come into and go out of problems at will. We don't need to worry about canceling them out. They're a little bit weird in that regard. So we're going to have this as sort of our number. Remember, we had a negative sign to begin with, but this, we will get a negative sign right here. Let me use a different color so you can see that. we're going to get a negative sign right here. So those two negative signs are going to end up being a positive value. So I'm going to make that a positive now in front. And instead of writing sine, we're going to write cosine. So we'll have cosine. And then we continue to write what was inside here previously. Okay, and so this is what we're dealing with. Now, because this was an indefinite integral, really we should be adding a plus c at the end. The College Board makes no mention of this in the grading key, and the video as well that they've done makes no mention of this, but I'm just going to throw that in anyway. And so if you do the math here and simplify a tiny bit, you end up with, rounded off to 2 sig fig, 0.18. And our units are still going to be m, although whenever we do calculus, we don't need to worry about units too much, but they do work out here, so I'd say be careful anyway. Times the cosine of 9.0 radians per seconds times t plus c. So that's what we're going to end up with for our equation for position. So just be careful with all of that. Again, there are a couple other ways of approaching this, but that's how I think it's most straightforward to be able to approach this. Next up, it does say calculate the value of k. What this lowercase k is, again, is the spring constant, of course. If we're going to use the most direct equation, that, in my opinion, the most direct equation we can use here, and the most direct way to do this, I actually can think of like 3 different ways that are completely valid and not totally off the wall that a student could solve this, but I'll give you the most direct way. Remember, we have this equation here and root m over k for a mass spring system. It's really important if you have an unknown under the root that the first thing you're going to do for this, let me write down this is a question mark here, and that's what we're looking for. I'm just going to say square everything. That's really by far the most straightforward way of proceeding with the problem, so just square everything. And so you end up with t squared is equal to 4 pi squared times m over k. Alright, and the question is, what's k? Well, at this point we can just switch positions of t squared and k, so I can rewrite this as k is equal to... Okay, and so that's how you would isolate, and then we can go ahead and plug in our numbers. Okay, and so if you do this, then you end up with a k value of 24 newtons per meter. So that's how you go about doing this section. Let's continue. Okay, and so now the FRQ shifts gears and we're talking about experiment 2. This last section of the FRQ is going to go a lot faster than the previous sections. So it says the block and spring is now placed on a rough surface as shown below. That's pretty important here, and so the block is displaced, the spring is compressed at a distance d and released from rest. On the dots below that represent the block, draw and label the forces, not components, that act on the block when the spring is compressed to a distance x equals d divided by 2. And the block is moving in the direction indicated below each dot. This, I believe, is a little bit confusing. If you're trying to work very quickly and efficiently, it's a little bit easy to just misread this and be like, oh, well, this is like our equilibrium line between both cases. Maybe we're saying this is moving like towards in this case, and it's moving towards in this direction in this case. That is actually not what it is saying. So be very careful. Notice it says towards the equilibrium position over here, away from the equilibrium position over here. So let me draw a little bit of a sketch to show you what we're talking about. It's kind of like here's the equilibrium position and it's moving towards. And then here is the equilibrium position when it's moving away. And in both cases, you're going to need to draw the free body diagram and the forces on the object in these 2 different scenarios. So be careful with this. It's easy to make a mistake that'll screw up the entire problem. I will say free body diagrams are some of the easiest points you can get on FRQs for AP Physics C Mechanics, but you do have to take a little bit of time to make sure everything is set up correctly. Alright, the first one you're going to write FG going down, of course, or you can actually write MG. A lot of times you can just write MG, and that will work as well. Going up, we're going to have a normal force, of course. Those are easy. So we've got our normal force here. Let's think about towards the equilibrium position. If it's moving towards the equilibrium position, first of all, what's the direction of the frictional force? Remember, we're set up to the left, so we're set up like right here. Here is sort of our initial position right here. And if we're moving towards the equilibrium position, then what is the direction of the frictional force going to be? Well, it's going to be to the left. So the force due to friction, we can label it as a generic force due to friction to the left, or you can call it a kinetic friction if you want. Now, what's the direction of the spring force going to be? Well, that's going to be to the right, and that should be drawn slightly bigger as the other one. Let's do the second one. So the second one, remember, we're still to the left of the equilibrium position, but at this point it's moving away from the equilibrium position. So if that would mean we're moving to the left. If we're moving to the left, what's the direction of the frictional force going to be? Well, the frictional force is going to be to the right. So we're going to say this is the force due to friction. And what's the direction of the spring force going to be? Well, it's also going to be to the right. So the spring force is going to be pointing to the right. So notice how there are two different drawings for the free body diagrams here. I think these are still easy points to get, but if you're careless or you're too stressed and working too quickly and not reading this closely enough, I can see why students could get this wrong. So be careful with that. Okay, let's do the last section, which is E. Okay, and so for E, it's still a continuation of experiment 2. It's really important to notice that we're actually using the same mass that we used in experiment 1. Not only that, we're also using the same spring. And so if you think about your equation for the period of a spring system, it's 2 pi root m over k, right? Well, if this is the same, like if the mass is the same, the k is the same, of course the 2 and the pi are the same, then the period is still the same. And it doesn't matter whether it's started from whatever position it started from, it still has the same period. It still has the same natural frequency or resonance, you could say. Alright, so what do we do with that? Well, we know that this is going to start in the positive direction, but it's going to lose energy over time. So we're going to start drawing this, and we're going to need to get a peak, but we also want to get, the period was 0.7 seconds, right? So it stands to reason that 1/2 of the period is equal to 0.35 seconds. This is how you can start to draw this out. I know I need to cross this at about 0.35, so let me see one. Okay, I need to cross right here. So I'm going to try to draw a graph that crosses right here. Now when I go to the next value, that needs to cross the middle axis line like right here. The issue is I need to draw this as a damped oscillation. That means it's getting smaller and smaller with time. Why is that? Well, there's friction in this case, and because there's friction, it's going to be losing value with time. Actually, I'm drawing dots here. Maybe I should go back and get rid of the dots. I mean, they're good in terms of, if you're working with pencil, they're good to kind of be your guide here, but they're not very good in the sense of, we probably don't want to have any extra material on here. So I want to continue to dampen this, and 0.35 plus 0.7 would be a little bit more than 1. So I'm going to try to draw this still dampening as well, to be dampening like right here. And then we can continue and end up with about 0.4 right here. So that's going to be our values. That's going to be our graph, how you would go about drawing this graph. That's how you're going to get your 3 points at the very end of this. So hopefully that's been helpful. That was rather long, but I really think that this is an incredibly valuable FRQ to think through and to reason about. So please know that I've done screencasts on an entire year of physics and basically an entire year of AP Physics C mechanics as well. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.